Hello and good day again everybody. Welcome again to Engineering Physics, and for this video we would now be discussing about work and energy. So when we say work as per defined in the definition here, as per defined here, it is once again defined as the measure of the amount of change that a force produces when it acts on a body. So these are to be our main points here. So amount of change and force. So these are to be the two main components of work. So amount of change and force. And for us to better understand what work is, so we have another definition here stating that work is done whenever a force causes displacement. So considering this particle here, suppose that this cart here is to be a particle. If we are to apply a certain pushing force here, so let's name it as force F. So the tendency of this cart is of course to move along the direction of the force. So in other words, of course, it would now be moving at this particular direction. Pero naiwan yung ulo ng F. One more time. So it would now be moving along this direction, of course. So with that, work once again is to be done whenever a force causes displacement. So let's suppose that this is now to be your force F. And let's say that if this is now to be its initial position, and once again, let's say that this particle is now to be moving towards the left, the right, I should say, and let's say that this is now to be its final position, and if that is now to be the final position, let's say this is now to be the final position, and with such, this is now to be the displacement, let's say D. So let's say that that is now to be displacement D. So once again, if this is now to be your force F and this is now to be your your displacement D, the mathematical formula for work, if this is to be the case, is basically equal to force times displacement. So basic. By the way, guys, I have abbreviated my work as WK, but in some books, they abbreviate it as just W. However, in today's video, I would be referring to work as WK for us not to interchange W for weight, because of course, weight and work are two different things. Okay, so for example, let's say that you have pushed, let's say this cart with a force of 6 newtons, and let's say that it has displaced 10 meters. So substituting known values here, F is to be equal to 6 newtons, and the displacement is to be 10 meters. So multiplying such without the aid of the calculator, we know that the answer here is now to be 60 Newton meter. So basically, this is now the work. But take note, guys, that Newton meter, so I would just be adding a note here on top, 1 Newton meter is to be equal to 1 joule. So 1 joule, or let's just say 1J. So with that, this is basically equal to 60 joules. So there, so that is now how we would now be computing for work. However, guys, take note that this formula here, so this formula is only applicable if your force and your displacement D are to be two parallel entities. So they should be parallel and they should be acting along the same direction. So as you can see, my force here is to be horizontal and my displacement is horizontal. But what if we would be having this particular setup? So credits to science.sbcc.edu for this figure. So as you can see, that the force F here is now to be acting about an incline, but the displacement is to be horizontal. Okay, so once again, if you are to solve for work, that should be force times displacement, but the force F and force D, displacement D, should be parallel and the same direction. And in this force system here, once again, your force is to be a vector, and once again, your force is to be a vector that has two components, namely, it has its own X component, and it also has its own Y component. And for us to solve for the value of work, we would just be multiplying the component that is to be parallel to, of course, our displacement. So as you can see, our displacement here is to be acting horizontally. Acted horizontally. And with such, if this is now to be the value for our f, let's say that this is now to be our horizontal component of f, and this is now to be the vertical component of f, it means that we will just be multiplying the displacement by the horizontal component, because once again, it is horizontal. But if, for example, that our displacement is to be vertical, we would be multiplying it with FV. But once again, as you can see in our problem, that our displacement is now to be horizontal. So with such, the work done here is equal to, so F, you can name this as FH or FX. So maybe I would just be renaming it as FX, assuming that this is now to be my X component, and this is now to be my Y component. So with such, Fx times dx, assuming that my displacement is along the X axis. Okay, and if this is now to be your vector, considering so katoa, if this is now to be the value of your fx and this is now to be your angle, so we would now be using cosine because of this abbreviation ka. So ka means that cosine theta is equal to adjacent side divided by the hypotenuse. And in this case, cosine theta is equal to, so cosine 30 degrees. This is to be equal to, so what is now to be the adjacent side with your 30 degrees? So that is basically fx. Divided by the hypotenuse, and in this case, the hypotenuse is to be 50 newtons. So 50 newtons. So rewriting this, cross-multiplying for me to isolate fx to one side, fx is basically equal to 50 cosine 30. So there we go. So substituting known values to our equation here, so wk is equal to 50 cosine 30 times dx, and our dx here is now to be 30. So solving for work here, so this is now to be equal to, looking at the calculator to your left, 50 cosine 30 times 30. So our answer here is now to be equal to 1299.038 Newton meter. Or we can also rewrite it as 1299.038 joules, since 1 Newton meter is to be equal to 1 joule. Okay, so in summary, so suppose that once again your force is to be parallel and along the same direction as with your displacement. The formula for work is to be equal to force times displacement. But let's say that your force is to be at an angle that is not to be parallel with your displacement. What you would be doing is that you would just be multiplying your displacement with the component of the force vector that is parallel and in the same direction as with your displacement. So in that case, if this is to be once again the case, wk is to be equal to, so f cosine angle times dx. So for pretend once again that in this force system, for this force system, for example, that the displacement is going up, and let's say that your angle is to be about the horizontal, work is now to be equal to f sine theta dy or fy dy. Having another example here. So suppose that we would be having a particle. So let's say that this is now to be a particle. And let's say that in that particle, a vertical force is now to be acting here. So let's say that this is now to be, let's say, your force F. And let's say, upon the application of force F, the box moved to the right. So as you can see, if this is now to be the initial position, let's say that this is now to be the initial position, it moved towards the right. Once again, it moved towards the right. So this is now to be the final position. Okay. So let me just draw. So let's pretend that this is now to be our displacement D. So as you can see, our force is now to be perpendicular to the displacement, because as you can see, our force is now to be vertical and our displacement is to be horizontal. So in that case, if the force is to be perpendicular with the displacement, work is automatically equal to 0. Because once again, your force is to be vertical, but your displacement is to be 0. So mathematically speaking, for us, once again, to prove it mathematically, if we would now be using this particular equation, which is, well, work is equal to force cosine theta times dx. So as you can see, our displacement here is to be horizontal, thus dx. And for this, for example, that this is now to be your force F, and your angle is to be measured from the horizontal, and if it is to be perpendicular, that is now to be 90 degrees. So basically, your work here is to be equal to F times cosine 90 times dx. However, if you would be solving for cosine 90, so looking at the calculator to your left, cosine 90 is basically equal to 0. So in other words, this is basically force times 0 times dx, and with such, this is now to be 0. And take note that this dx here is to be the displacement along the x direction, and this is not to be derivative. Just so you know. Okay, so once again, if your force is to be perpendicular with the line of action or its displacement, the work done in that case is now to be equal to 0. Okay, so if you are now wondering, is there a time whereas if let's say that you would now be applying a force F here, the displacement would now be opposite it? So suppose that we would be having a special guest here named Michael Jackson. So as you can see, he tried walking towards the right, but his displacement is going towards the left. So if that is to be the case, the work is now to be negative. So we would be having a negative work once again if, well, just like MJ here, he is walking towards the right, but his displacement is now going towards the left. But disclaimer that this is to be a bad example for our topic, because what MJ is doing here is just to be an illusion. So its force, his force is actually going towards the left. And once again, that moonwalk wherein he seems to be walking towards the right is just an illusion. Okay, so for us not to compromise engineering physics, let us just have this as an example. Okay, suppose that there is to be a car, and let's say that this car is now going towards the right at a constant speed. So once again, its motion is now going towards the right. So if this is now to be the car, of course, it would now, it is now moving here at this particular direction. Okay, so anyway, if it is now to be moving at a constant speed, the driver decided to apply the brakes for it to stop. Let's say, for example, that this is now to be its initial position. And let's say that the driver want the car to be at rest at this particular position. And let's assume that this is now to be 15 meters for pretend. So there, if it is now to be moving along this direction, if you would now be applying brakes, what happens here is that there is now to be a force applied here for the car to slow down or for the car to decelerate, so that once that the car would be reaching this particular position here, it would now stop. Okay, so as you can see, in this particular case, the displacement is going towards the right, but the force is now going towards the left. And with such, we would now be having a negative work. So let's say that the force applied here is, let's say, 5,000 newtons. So by the way, guys, I'm not quite sure if this is to be accurate. This is just an example, but for pretend that a total force of 5,000 newtons was applied opposite to this car for it to stop at this position. So with that, the work done here is to be equal to 5,000 newtons times 15 meters. But take note, if they are to be opposite to each other, so once again, as you can see, the force is pointing towards the left and the displacement is measured from left to right, so magkabaliktad sila, you would now be applying a negative symbol here. So with such, the work done here is now to be negative. So looking at the calculator to your left, so negative 5,000 times 15. So with that, negative 7,500 Newton meter or negative 75,000, joules. So this is now to be our final answer for this particular situation. Okay, so PS. So as you can see, that work is now to be dependent kind of to its direction. Take note that work is actually a scalar quantity. So it is not a vector. So once again, work is to be a scalar quantity. It means that it does not have any direction. So it would be as simple as that. So it might get confusing in a part that we are considering directions here, but for its product, once that you have multiplied the vector and its displacement, it is now a scalar quantity. So take note of that. So once again, work is to be a scalar quantity. So there.